All right. Okay. So the course is social network analysis. Sometimes we called previously network analysis for linguists. Then we called it like linguistic network analysis. Somehow, social network analysis got stuck as a name for this course. But in general, what we're going to be doing is going to be talking about network analysis or approach through networks to analysis of both social networks and a lot of sort of linguistic, a lot of text information and whatever can be represented as a network. So the idea is that in the several lectures, I'm going to talk about the instruments, right? The tools, about the approaches to network analysis. We're going to talk about, what type of networks exist out there and their properties. And then we'll try to focus a little bit more on the linguistic side of the things. And that's sort of our first module. We'll also have seminars where you're going to go through practical exercises, working with text and networks. And then the second part of the course, the second module, we're going to run it more as a project/journal club, where we're going to discuss various techniques and research papers on the topic. Okay, so again, like first module is more about learning approaches, methods, tools. Second module is research type of discussion. All right, can you see this? Can you see my screen? Yep. Okay, good. All right. So class technicalities, I'll be teaching the class. Ilya Makarov will be doing the labs/seminars, and I think they're scheduled right after the lectures. And we have a Telegram channel. I think you probably all subscribed onto this channel. So regarding assignments, there will be labs that you'll need to complete. There will be paper discussion, and there will be some course project that you're going to do next module. So the schedule is here. There is a website where I'm going to publish some papers. They're going to be the lecture slides are going to be there. I'll probably share it in Telegram too, and recordings of the lectures will also be there. My email, Ilya's email, Zoom as an online collaboration tool. Now it's a Python-based course. So we're going to be using IPython notebooks. I strongly recommend you use Anaconda distribution that has everything and just works nice. For text processing, of course, in LTK, I'm sure you're familiar with that. I might learn a little bit, might use a little bit of scikit-learn for a few things here and there. And NetworkX as a library for network analysis. I typically, Python is still not so good for visualizing large networks. And so there's some open source visualization tools, free visualization tools. One's called YED, another is Gephi. There's the two programs you can download and use for visualization purposes when you need to look at large networks. So that's sort of those technicalities. Any questions about those, the process? Okay. All right. So the topics we're going to cover, and there's like literally 4 lectures. The topics we're going to cover will be, the first is today lecture. It's an introductory lecture. Plus, we'll talk about statistical properties of the networks. Next lecture will be about what I call network nodes and link analysis. So how you kind of look at the links, how you calculate certain type of ranking for the nodes. So literally how you analyze the structure, like local structure of the network. Then the next lecture would be about community detection. This is probably one of the sort of most popular topics in network analysis: how to detect communities or groups of nodes that are tightly connected among themselves. And then we're going to talk specifically about network visualization and sort of various types of networks. All right. So network science by itself is kind of it's a new science. In the sense that it kind of started forming as a science and as a scientific communities. At the end of sort of last century now, right? At the 90s, and it formed from different sciences. And you'll actually notice the influence of those sciences on network science. And you will notice that papers on network science has been published before, and it's actually still being published in, for example, physics journals or mathematics journal, economics, in bioinformatics. These are all sciences from where scientists who are now working on network science came from, that their origin, and they just keep using those journals to publish things. But at the same time, there are very specific network science dedicated journals and conferences exist right now. But again, if you think about sort of probably the very origin of network science is, of course, in sociology, social network analysis. That goes back to mid 20th century works. Then there is, of course, mathematics, where people talk about graphs, computer science, graphs and networks. Physicists like to talk about complex phenomena, and so they usually call it complex networks. And then there is economists, there's bioinformaticians, et cetera, et cetera, et cetera. So there are like a lot of different disciplines that focuses these days on using this network representation of knowledge. So because it came from, network science comes from so many different disciplines, there is also some duplication in notations and terminology. And you will hear me often referring to network as a network, or sometimes as a graph, and it's the same. We call nodes vertices or actors if that comes from social network analysis. Links can be edges or relations. Sometimes people talk about communities, but sometimes people call it clusters. So there is a lot of this, and eventually you will notice how that terminology propagated from different fields, and you can actually, by looking at what people call certain things within network analysis, you will actually understand what sort of subfield, what field of science they came from. There are a bunch of examples, and in fact, when I started teaching this course, probably 10 years ago, I had to show closely, like, sort of, okay, this is what network is, and that's sort of what we're going to talk about. Today's, everybody understands what social network is, and I'm sure you guys are, I'm sure you have accounts on a bunch of the networks, right? So it's not surprising that you can see this is an example of social network where there is what we color coded. The color code is, community is color coded. There are friendships are edges, nodes are actually people, and this is someone's friendship network where the person is shown at this big node in the middle, and then there are different types of communities surrounding this person. And here is, for example, LinkedIn map, also like this egocentric network, and there are communities, groups of nodes that are tightly connected to each other, right? Color-coded. And here is an example of, for example, co-authorship, where, there is, and if you notice, there is always a reference to where this comes from. This is, International Committee of Intellectual Cooperation, where there is, 1,723 nodes here on the slide, and they're connected when they worked on the same type on the same document, right? So it's co-authors. Again, please notice visualization, the way it's done, where there is a size of the nodes proportional to the number of connections. And then there is this very tricky job of laying this out. Laying out means positioning the nodes on a picture, right, on this dimensional plane, such that you can actually see something. And you will notice later on when you start plotting networks that this is probably the most challenging task in network visualization, is how to place the nodes such that you can actually see the relationship and see them clearly. All right, so here's another example where we have, it's in fact from Twitter. I'm sorry, that's not Twitter, this is political blogs. And this is how blogs refer to each other, right? So color-coded is conservative versus liberal. And if you notice, it's kind of entertaining for those who are in political science to realize that, in fact, conservatives, of course, mostly reference conservatives, liberals mostly reference liberals, and there is a very, very thin layer of blogs, which means people who kind of look in both direction, right? Try to keep it in sort of balanced. Here is another example. This is a Twitter. And this is how news spreads on Twitter. Again, here is the edges are followers that being activated when they retweet, and every node here is a tweet. This is a very famous data set, which is called Enron data set. Who guys do you know what Enron is? Okay, yeah, so Enron was a US company, energy traders at the beginning of the probably 2000 something, early 2000. And there was a huge scandal because those guys were inflating prices, doing insider trading and a lot of other things. And so eventually the company collapsed, and there was a big lawsuit. And because of that, their internal communication and emails became, were presented as an evidence in the court, and because of that, they became available online. And that was like first corpus of the emails that became available online for researchers. And so researchers were extremely happy because the emails actually contained all the text, of course, communication, but they also contained all the links, right? So you know who wrote what to whom and when, right? And so that became actually a very, very, it became like one of favorite data sets for like network science / language sort of processing guys who wanted to know how people, for example, influence each other and how they communicate. Anyway, this is a visualization of that Enron data set. You can actually search for it. Just type Enron, email data set, and you'll find it easily. Here, obviously, the nodes are people. Edges are communications or emails sent between people. The size of the node is the intensity of communication, sort of total number of emails in the data set. So when you look at this network, at those networks, you might notice a few properties. And on the right-hand side, there is one of those type of networks. You might notice that, they're sort of not regular, right? But at the same time, they're not completely random. And so topology, which means, the connectivity patterns are not trivial in the sense, you don't see such a very regular structure. And you see, maybe you kind of realize there is a little bit of like fractal structure. You zoom in, you see also quite similar structure as when you sort of zoom out. The most amazing part about networks is that there are a lot of properties of those networks that are quite universal. And universal means, there are networks that comes from biology, there is a transportation network, there is like email network, there are language networks, there are, well, you name it, networks. But they do have very, very similar statistical properties, like sort of amazingly similar properties. And that's actually why physicists love the science of networks, is because physicists usually try to find some universal laws that describe phenomena, and it feels like there is some sort of universal, something unique and universal happens that generates the networks in the very different fields that have very similar properties, all right? And so we're gonna touch upon this. And that's why it's a complex system in the sense that there are, like the same way as a human body, right? Where you can, by learning just what, for example, the properties of the human of the cells of our body will not actually explain the behavior of the human, right? You actually need to study a human as a human as a whole, right? And so the complex system means really that we can study and investigate every node independently. We can look at every edge, but by looking at them, by deconstructing it into that level, it's not going to help us to understand the behavior of the network as a system, right? So we need to study the network as a system, like holistically in its entirety. And so that's where this word complex, our complex systems come from. So there are really, as I mentioned, there is a sort of universal properties, right? And there are three major properties, major universal properties that complex systems or complex networks have. One of them, the first, is this very specific node degree distribution. We're going to talk about it in a moment. The second is what's called small world property, or small diameter, or 6 degrees of separation. You probably heard about this. 6 рукопожатий. And then the third property is this high clustering coefficient, or high transitivity of the networks. In fact, if there is one thing I want you to remember after this lecture, is that those three properties, right? So when you talk about networks, there is this usually three properties that are quite universal across all the networks out there. Okay. So we're gonna dive in right now into those properties so you would understand a little bit better what I really mean. So first of all, distributions. Now, if we try, to measure, for example, take a group of people and try to measure the height of every person, right? Then you're going to get some distribution, right? There will be a few people of maybe 100 and I don't know, 70 centimeters, and then there'll be some 165, then there'll be 100, 85, etc., etc. This distribution might actually have two peaks, for example, for males or females. But if we combine it, there's going to be some distribution, and this is usually sort of very similar to Gaussian. And the idea is that there is a very very clear expressed peak in the distribution, right, where majority of the people have the heights, and then there are very, very quickly decaying tails of the distribution. So most of the people are within, couple sigmas, within a sigma actually or maybe a couple sigmas of the mean of the distribution. So which actually in pure Russian, or I'm sorry, in pure English, it really means that you can hardly meet somebody who is 2.5 meters tall, right? Maybe some person somewhere, but very rarely. And I'm sure you're not going to meet anybody who is like 6 meters tall, right? Any human. And the same thing, yes, there are people, with diseases that are maybe 1 meter height, but they're just, again, this is a disease problem, right? So majority of the people are, the heights are centered around, 100, probably 7 meters 70 or meter 75, right? So this is a distribution, and a lot of things in the world distributed that way, but not all of that. And the power law distribution is a very, very different distribution. If you kind of just to connect things, with language, for example, it's ZIP or ZIP distribution that is type of power law. Did you guys hear about ZIP distribution? You're familiar with that? Can you remind me what that distribution says? What is it? What's ZIP law or ZIP law? Oh, come on, don't be shy.
Просто ответите. Он, в общем, про то, что в каждом варианте цифра для слов количество употреблений слов обратно пропорционально их номеру в упорядоченном по частоте списке, но фактически это не только для слов соблюдается, но и для других явлений, которые могут быть более или менее частотными.
Yes, you're absolutely right. So the idea on the ZIP law is that if you take the frequency of, for example, of the words usage, and then you rank all the words by the frequency, right? Then the frequency of the appearance of the word is inversely proportional to the rank, right, in this table. So, but that's not only, again, this is not only ZIP law, right? So, for example, if you look at the populations of the city and you just try to for example, count how many cities have what population, you realize that there are several cities with a lot of people, but the majority of cities have very small population, right? And if you think about Russia, yeah, pretty much everybody lives in Moscow, right, these days. There is the population of the Moscow is clearly dominating. Now, if you look around the world, that's exactly the same situation, where there are a few cities that are like really huge, and then the majority are small. So if you look at this type of distribution, it's called power law distribution. And in general, the general form is that it says a probability, or the frequency, or the probability, if you normalize probability, if you don't, it's frequency, of something is inversely proportional to that number in some power, right? And gamma is that coefficient, and that's why it's called power law. So for example, gamma can be 1, and then it is just over C over K, right? And that's Zipf law, but gamma can be any other number. And so I would say that the frequency of how many, for example, or the probability to meet, to encounter a city with 1,000 people is going to be proportional to some coefficient divided by this population to the power gamma. So that's the idea. Now, this law, if you look into, if you draw it on the regular scale, is going to look like on the left. The interesting part that if you actually take logarithm of this expression, right? You take log, then the power law will actually look as a straight line on a log-log scale. Does this make sense from these formulas, guys? Yes, no, sort of, kind of. Okay, so what I'm trying to say here is if your x-axis is log k and your y-axis is log f of k, then on this axis y versus k, it's going to be a straight line. And the reason for that is just because if you look at this, at the formula, then the logarithm of the product is equal to the sum of the logarithm, and the logarithm of some number into the power is equal to that power times the log of that number, right? So sort of basic math. All right, we're gonna look into, we're gonna encounter this many, many times, so you get used to this. And there are, there is plenty of those power law distributions out there in the world. Like you said, the word frequency is clearly following the, and this is log-log scale, right? So you expect to see here straight lines. So the word frequency, it's on the x-axis, it's again, it's logarithmic axis, so it's a logarithm of word frequency, right? Versus how many times in how many books it happens. Citations. There are some books, there are some works that are extremely popular, but there is not that many of them. Majority of the works are not that popular. And books sold, and web hits, and earthquake magnitudes. There are tons and tons of phenomena out there that follow this power law distribution. And sometimes it's also called the long tail distribution. So again, the quantity of interest, for example, the frequency. Now we're going to talk about networks. So for us, what's important is the frequency distribution of node degrees, right? Node degree is how many neighbors node has, right? So how many friends you have. And the interest for us is the distribution of the number of friends each person has. You can think about number of friends, or if you think about, I don't know, Twitter, it's number of follows, or Instagram, it's number of follows, or, whatever. If you just think about this, what do you think the distribution is? I mean, actually, you already know the answer. It's written here. There are celebrities who has tons and tons of followers, like thousands and thousands, millions of followers, but there is not that many celebrities. Majority of the people have few friends, right? And how many friends do you, like each of you guys, how many friends do you have on Facebook?
Maybe 200.
200. Okay. Who else? Who more? Who has more? 500. Who has 500? Oh, you guys are a shy crowd. All right. So you know, it actually, like, you know, typical on Facebook, there was really like a couple hundred friends, right, for a normal person. Now, there are some people who are quite lonely out there with very few friends, and there are quite a lot of those people. So that's what majority is. And there are a few people who have just, you know, a lot of friends, but those are, you know, either fake friends or like, you know, celebrities with really fake friends. Anyway, so that's the distribution, right? And that's a power law. Very similar picture for citation of papers. When you take a, you know, scientific paper, there are some papers that are extremely popular, and they have a lot of citation, but there is very few papers like that. And the majority of the papers will have very few citations. Now, this has been noticed in the paper by Derek Price in 1965, right? So this power law distribution, you know, goes back to this 1965, and actually, in fact, there's also Anatole Rappaport 1961 when they studied percentage relative number, total number of cited papers by different, you know, from the subset of papers published in 1961. Now, can you think about mechanism? Why would that be happening? Why do we get some papers that are extremely cited, and others kind of obscure and almost not cited? What's happening?
To my perspective, the more significant the paper, the more it gets cited. So
yeah, I mean, look, of course, there is this notion of like, yes, somebody wrote a brilliant paper, and it's probably eventually get cited. But what's interesting is how fast this, and you know,
the more it's cited, the more people get know about this paper, and it becomes more cited and more cited.
Yeah, exactly, that's what I had in mind. There's this sort of self-fulfilling prophecy, which is, you know, the money goes to money, right? In some sense, you know, the paper gets noticed and gets cited. There is another paper with maybe similar results, but it was not noticed. Now, the paper that got cited, now more people read the papers that are citing it. So, okay, that's the paper. So they start citing it, right? Sometimes without reading. If you actually write papers yourself, you realize people not very often kind of go and trace down to the original source, right? And so, and that sort of snowballing effect. And that's pretty much what magnifies some papers to like fame, and others goes to obscurity, though they might be originally, first of all, they start with on the same basis level, right? No citations, and they might be quite similar in the quality and the discussion. And in fact, there are so many stories about this in science. Even like if you think about, you know, the famous deep learning, there are people who are extremely famous now because their papers were cited, and now they cited as the fathers of deep learning. But there is sort of another person who actually wrote papers to be at the same time, but somehow, you know, he doesn't get the fame, right? But if you go back, you know, 20, 30 years back, you realize that back then his papers were as influential as these guys, right? So that's the magic of this sort of you know, the sort of enhancement, right, that happens due to this you know, citation and the power law, right? So that's the power law. That's where it comes from. I mean, at least I would say in the citation, that's sort of the mechanism, right? It's much harder to understand what the mechanism in biology or other networks, but in citation, right, this is probably why some papers, why we get this very uneven distribution, right? So you can also think about, and I think I really like this slide and this picture, and in fact, this picture is from the textbook by Albert Barabassi, and I strongly recommend the textbook for this course. It's available online, and it's actually quite good in terms of the sort of the level of the scientific rigor and the sort of the readability of the book, right? So what you see here on the right-hand side, it actually gives you an example of power law network, which is airline network. Well, at least it used to be before the COVID, right? You do have major hubs, right? And those hubs, there are very few of them in the US, right? LA, Chicago, Boston, you know, Atlanta. and there are lots and lots of flights goes there, right? So they have lots of connections. And then there's like very many small cities where flights go to, but there's like one, two, three flights go to those things. So the same thing actually in Russia, right? There's Moscow, which is a huge hub, like everything flies to Moscow, but then there is like you pick up, you know, any other city, there'll be like very few flights coming out. So it's very uneven distribution in terms of number of flights getting out of the city. And what's on the left is a sort of simple visualization that allows you to understand, and it just shows you those connections, just shows you like, look, on the x-axis is a number of links or a number of friends or node degree, right? On the y-axis, it's how many of the nodes of those type exist. And so what it says is just, if you go to the left on this picture, by the way, I can probably, just give me one sec. No. All right. Sorry. It's not allowing me to easily show you. All right. So if you go on the left of this picture, there are a lot of nodes with only a few links. And on the right, it just shows you a node with very many links, but it says that, you know, there are very few of those nodes in the network, right? And so the same thing with the social network. Again, a lot of people with a few friends. I'm sorry, yeah, a lot of people with a few friends, and, you know, very few people with many friends. Okay. So this is an example of this power law, and this is how you spot it on a graph. This is actually very cool site. It's History of Philosophy, and the way, you know, to understand this is different philosophers, they shown as nodes, right? And then for each philosopher, there is a connection to another philosopher if that other philosopher follows this guy, this first one follows sort of his teaching, right? Follows his philosophy. And if you look in this, well, I'm sure you notice familiar names there. Anything surprising? No surprises? So for me, honestly, again, I'm not a philosopher, right? So, but for me, what was extremely surprising to see that Karl Marx has as many followers among philosophers as, for example, you know, Plato, Aristotle, right? Or even, even Kant, right? Because here, again, the size of the node is the number of followers within the philosophy world, right? Number of philosophers that follows this philosophy, right? Follows his teaching. So for me, it was like, wow, that's pretty big, right? Anyway, so the point is that, again, if you look at this, you realize that when you have a power law distribution, there are some nodes, you know, some people who have a very high degree, who have very many friends, very many followers, but the majority of the nodes in the graph have low degrees, right? So there is this very strong difference in between, you know, those who have everything and those who have nothing, right? I mean, if you think about economics, it's the same principle, 80-20, or even more skewed. You know, how many people have majority of the wealth and the rest have very little money, right? So it's the same principle. It's a Zipf law, it's Pareto law. You know, there are different names of this. In the networks, it's expressed as a power law, which is, again, few nodes with very high degrees, which is lots of connections, majority of the nodes with low degrees. Now, mapping it into, for a second, let's say into language, if you think about every word being a node here, and an edge will be placed in between two words if those two words occur next to each other in a sentence, right? Think about this concurrence network. Which words would have high degree? the words that occur with many other words, right?
Articles.
So what are exactly. Articles in English is probably and or or a, right? In Russian, I don't even know what it's going to be.
V.
Yeah. Maybe you guys will have a chance to check, right? And that's part of this course, to actually try to analyze this and see, the positioning of the words. Okay, so that's one story, right? This power law distribution. Second story comes from sociology, and kind of the first person who noticed that and dedicated a lot of work to it is Mark Granovetter, and where he looked in the social networks and published this famous paper, The Strength of Weak Ties. It's actually the paper about job search. So that suggests how you need to look for a new job, and literally saying that you need to use what's called weak ties instead of strong ties when you're looking for a new job. Because strong, and I'll explain in a second why that's the case. So what he said is strong ties are those ties that are, or those friendships that are used very often, so they're strong, right? The connections are strong, that's a close friends. And weak ties are those that are kind of, used once in a while, right? So this kind of your friends, you probably have it in your phone book, but you call them maybe once a year, like say Happy New Year, right? So the point he was saying is the following, that when you have a social network, and you have this kind of scenario, A, B, and C are people, there is a tie in between A and C, right? Strong tie, and there is a strong tie and between A and B. It's impossible to have, right? You cannot have strong ties in between A, B, A, C, and not have a connection between B and C. So he pretty much was saying that, guys, in the social networks, there are triangles, right? You're not gonna have strong friendship between person A, B and person A, C, and person B will not know person C. And just think about your friends. Most of them most likely know each other, right? And that happens because you either were introduced to them that way, or somehow you introduced your friends to each other, or maybe you're mentioning one person to another in your discussion. So if you have strong friends, strong relations with people, they usually know each other. And that forms these triangles. And there are a lot of triangles on social network. So humans, do that. And in fact, so what Granovetter was saying in his paper, that, look, you don't look for a new job following strong ties, because you kind of remain within the same community of people all the time, right? You need to use sort of long-range weak ties to look for new opportunities, in life. But anyway, so the idea is, again, the main point of his paper is that when you look at the social network, it's about triangles, and there very rarely you will see this kind of arrangement, this A, B, C, which is sort of open triad, and he called it forbidden triad. All right, this is 1973, which is, man, like what, 50 years ago, right? And this is, for example, an example from Facebook, from data science team at the Facebook, where they looked at, for example, friendships for the person. This is a central person, and they talked about like this all friends relationship and maintained relationships. Maintained meaning, people communicate a lot, and you realize that you see lots of triangles in there, right? Triangles here, there, triangles. Here is quarter network, and which also has quite a few triangles, for the obvious reason, usually quarters know each other pretty well. And here is, organizational network, where people in organization, of course, you work with people, so people know each other. So there's also triangles. So social networks do have a lot of triangles. Now, another word for this triangulation of the network for a lot of triangles is called transitivity. And transitivity really means, if A knows B, B knows C, then A will know C, right? So it's a transitivity property from the mathematics. And so that's what's also used here. So the point is, social networks have high number of triangles. And there is another word for this is transitivity. And then there is another word for this, is also called clustering coefficient. Now, that often causes confusion, but when people talk about clustering coefficient, they usually talk about the fraction of triangles in the network. And that's the ratio of the total number of triangles to the total possible number of triangles. So, and we're going to look at the formulas a little bit later, but that's sort of the words, right? That's the terminology. And finally, there is this third property that I want you to know about. This is a 6th degree of separation, right? Or small world property. How many of you heard about this experiment? Yep, 1, 2, yeah. So it's a famous experiment by Stanley Milgram, and Stanley Milgram, actually he's famous for another experiment. Do you know what other experiment he's famous for? All right, this is a dude who set up the Stanford prisoners experiment. And if you don't know about that one, read about it, because that's like scary, fascinating thing. I mean, I was amazed that he was actually even allowed to do this, right? Today, I'm sure nobody would allow in any university to run that type of experiment. Now, this is much sort of safer experiment. Here, he just tried to understand how people know each other. And so what he did is he published in a newspaper an ad saying like, look, guys, I want you to participate in an experiment. I want you to send a message to a person. This is exactly his ad, right? So an instruction for participants of the experiment. So he said, look, I want you to send I want you to send a letter to and deliver a letter to a person. You don't know him. What you're allowed to do, you're allowed to send this letter to any of your friends, right? Any people you know. If you think that will shorten the distance to the address, to the final recipient, right? But and that's what it says, right? So, and you're allowed to send it to this final person only if you know him on a personal basis. And so the idea is to trace the letter that goes from friend to friend to friend. Now, today it's very easy to do, right? You can just try to forwarding emails until it reaches the right person. Though of course, most likely it's people will not do it because it sounds like a spam. But back in the days, and again, this is 50 years ago, more than 50 years ago, that what they wanted to, he actually published a real ad in the newspaper and asked people to actually fill out the cards and send out for the participants. Send out those cards. And so he, the target person was living in Boston, and the people who were supposed to send him letters, he picked up some number of people in Boston and some number of people in Nebraska, which is like middle of United States. And so then the important part of the experiment was to actually keep a ledger of the letters. And so when somebody receives a letter, the letter would also says, okay, it went through 2 people or went through 3 people or went through 4 people, right? And amazingly that actually worked. And and by the way, this is a map. So he recruited 296 volunteers, 217 letters were sent. They knew about the target that was, Boston stockbroker. There was no name, address was known, but they were not allowed to send it to this address. It was known, where he lived, where he went to college, what was his hometown. And then the question was like, okay, the goal is to deliver the letter to him without sending to him directly and sending through, your friends you believe might know him better, or being closer to this person, right? Who you do not know. So this is literally the experiment to measure how well the world is connected, right? Through friendships. And the amazing part that, 30% or 29% of the letters actually reach the target, right? Through this sort of hands from hands to hands, right? And the average chain length they measured was like 5.2. So letter went through 5 people on average before reaching the target. And that's where the 6 degrees of separation, the phrase came from, right? From this experiment. After that, there were many other experiments. And of course, when social networks started, there were like lots of experiments confirming this. For example, there was an experiment 2001 that was on emails actually, with sending, using a lot of senders. There's of course Microsoft Messenger graph at some moment, that there's a Facebook graph, etc., etc. Interestingly enough, on the Facebook, of course, this is the largest experiment. Back in the 2012, when Facebook was a little bit less than 1 billion users, they measured the separation, right, average distance from one person to another on Facebook, and it was like 4.7 sort of handshakes, or just 4.7 people on average. And interesting that it is shrinking, right? As Facebook growing, Facebook world becoming smaller and smaller and smaller. So that's yet one other property of the network, which is sort of amazing, because there are almost 1 billion people. And what this experiment says is that on average, if you pick one random person and you pick another random person, you need to go only through 4 nodes to reach that other person, which is amazing, thinking about that there are 721 million people in there, right? Think about this. I don't know, if you have 100 people and let's say each know only 4 people, right? And they're like sort of live on a grid. That will take at least 10 steps to go from one end of those, sort of cells to another. And you have 700 million and it's only 4 steps, you're only 4 steps away, right? And so that really means that you're, say 4 to 6 steps away from any other person in the world on average, right? There are some people who might be much harder to reach, but this is amazing. And surprisingly, there is, you would think that this is like impossible, right? Like totally impossible. But there is extremely simple mathematical models that show that, in fact, this might happen. So that's not like completely entirely crazy. If you think about this, and let's just look at this very, very simple model. The model has every friend, and in this picture has 4 friends, right? And the only thing I make here, the only assumption I make here, that these friends do not overlap. Now, this assumption contradicts the triangulation story I told you before, but let's for a second make that assumption to make simple computations. So if first person has 4 friends, right, and each of his friends have 4 friends, then second degree is going to be 16 friends, right? Then each person on the next layer has 4 friends, then it's going to be 64 friends on the third layer, right? Okay. Now, let's assume that the first person has 10 friends, then on the second step, it's going to be 100 people you can reach. On the third step is going to be 1,000 people you can reach. On the next step is going to be 10,000 people you can reach. And that's only 4th step, right? And then it's going to be million. So this kind of setup has extremely fast growth. And it's exponential growth. In fact, that's the same way as COVID growth, right? Very, very fast. And so you can easily estimate that, if I want to cover 6.7 billion people, and let's say each of us has 50 friends and they don't overlap, it will actually take only 5.8 steps to connect all of the people. If people were living in this type of a model, right, the sort of centralized. Now, there is, of course, overlap, and so, it takes, maybe not 5.8, and, you on average have more than 50 friends, but it just shows that this is in fact possible if there is a very particular structure of the network. And this is an example of this structure. And those networks that, the language network, friendship networks, they do have that type of structure. And this is called small world structure. All right. So what do we see? Well, we see that there is this three major properties, and I forgot to put that slide in. Where they are, here they are, right? There is three major properties that you want to know about networks. One is this power law degree distribution, or what's called scale-free network, which is that you do have lots of nodes with low degrees, and you do have a few nodes with high degrees, but those are very, very high degrees, right? So this very, very skewed distribution. Then the second is the small world property, right? So 6 degrees of separation, 6 handshakes that separates the world, whatever you call it. But the fact that within these networks, you can very quickly get from one node to another. So the distance along the network is very short, right? That's the second property. And the third property is this high clustering coefficient, right? So there are lots of triangles in the network. It's also called, again, transitivity. So it's a high transitivity. So these are three important things you need to remember about those networks. And in fact, like most of the networks have this property. Any questions? All right, okay. So, your guys linguist, so you probably know this better than me, right? I'm not a linguist, but I want to give you a few examples of the networks, how they might work in linguistics. And in fact, the goal for this course is for you to learn and to discover how the tools, how those properties we're going to teach you, right? How those approaches might work for linguistics, right? So that's literally the goal for the course. So I'll give you a few examples of the networks. There's a word co-occurrence network, right? Which is the word precedence. Then you can think about semantic networks. Then you can think about syntactic networks, right? So let's look at a few of them. Let's say this is a co-occurrence network, right? Where what you do is the nodes are the words, and they're connected by the edges, and they're connected is one word occur in the sentence after another word, right? Now you can actually here build very different type of networks. You can build only those networks. You can make, or you can count only those connections when one word follows another word directly, or maybe it can follow, through a few other words. It doesn't matter, right? You can build it. You can remove stop words. You can do whatever you want. It's your network, right? And then you can build it as a directed network, and then you preserve the sequence of words in the sentence. Or you can build it as undirected network and just pure co-occurrence. This is what you see here is this word precedence relations, right? So this is where you literally look into one word following by another. And it's kind of funny in this picture, you can actually just start somewhere in the graph and start walking around, right? Just following random walk, and it will generate different sentences, right? Now, if you look here, it's the most sort of well-connected and the highest degree nodes are with article A and then the preposition to, right? Which is sort of obvious. All right, so that's one type of networks. And this is network generated by a few sentences. So that's why it's so small, but you would expect you can just take, War and Peace and run it on it. In fact, by the way, and that's what we did a few years ago with guys, you build the networks for different authors, and you realize that different authors have very different type of networks, the way they use language, because the networks reflects how somebody uses language, right? And some people are much more, I'll say, fluent with language, right? And they can put together sentences that others will not. And so you will see the network will show you, you can actually distinguish authors by the sort of average network of their, that built on their books, right? Okay, so of course, you can build the syntactic networks, right? When you parse the sentence and then you actually connect things. You can build semantic networks. This is less automated because I think there is probably still not a good way to automatically build a semantic relationships, right? But there is Caesarius, right? Thesaurus that have semantic relationship. Correct me if I'm wrong. Do you know if there was any way to like automatically build like, the networks that show you, semantic concepts? I don't know. I mean, so that you guys quiet means you don't know, they don't exist.
Maybe we can take dictionary definitions and use it as a text to make a coherence network.
No, I mean, of course, now look, if you take dictionary, yes, the dictionary will give you like, okay, these are synonyms, right? Or there is an antonym, but they have to be like, it's us human who create those dictionaries, right? They're not like automatically created. It's sort of, we decide which words are synonyms and which are not, in some sense.
We can build the graph out of the vocabulary that was learned by the word2vec model, for example.
Okay, that's actually that's an interesting thing. I'm just actually wondering. I mean, I'm wondering if word2vec will be smart enough, right, to group together, synonyms. I mean, it feels like it should, but I don't know if it is good enough to do that, right? Because I mean, again, word2vec, the idea is, right, it puts your words in a context, right? And you would say that, yes, you can probably pick out synonyms if they're replaceable, right? If they're kind of within the same context, just use different words, then they might be synonyms. So it could be that it works. I don't know. I never tried, but this is something, one of the projects, you guys can work on. Okay, so the point is, again, coming back to this story of properties of the networks. This is from one of the papers. The authors look at, different network types. They look, I believe this is probably for English. So there is a concurrence networks, syntactic networks, semantic networks. And they look at the different size of the networks. This is just sort of the size of the experiments, right? Nothing else. And then they measured the degrees, the average degree on the network, right? They looked at, and you notice that there is, degrees from 4 to 8, 5 to 10, 10 to 4. So there are different node degrees in those networks. The type of links, functional meaning. Interestingly enough, the path lengths. Notice that the path lengths in those networks are actually quite small, right? It's 3 to 4. Then they look at the clustering coefficient, and we're going to define in the next lecture how you measure that. But what they're saying is like literally, let's compare number of triangles in the network compared to the number of triangles if the network was completely random, right? So imagine that you have a bunch of nodes, or like bunch of words, and they're randomly connected, which means, when you generate sentences, they would like sort of randomly the words randomly following each other, right? And so they realized that the number of those triangles will be 1,000 times more in those language networks than if there were sort of meaningless connections in between words, right? And then the link distribution, this is exactly this power law, and the gamma is that coefficient, right? So the frequency, the probability to meet a particular word, or within this network, the probability of the node degree is 1 divided by the degree to this power gamma, right? So it is 1 divided by, k to the power 2.2 or 2.4, right? So it is not, zip floor is gamma equal to 1. This is gamma equal to 2.2. Interestingly, they notice that in the concurrence networks, the hubs, and hub is a node with a lot of connections, like high degree node, right? They're saying hubs are words with low semantic content, right? So, наверное, предлоги, articles and prepositions, so low semantic content, but they used a lot of places. And so they are the nodes of high degree, which are called hubs. In syntactic networks, it's the functional words, and in semantic network, obviously, it's polysemy, right? Polysemous words, right? Those, they become hubs. And interestingly enough, when you build those type of networks, there is a question, okay, and what happens if you sort of remove some of those words from the network, right? Let's kick them out of language. And, for example, that's the results that causes. So this is an example, in fact, of how you can use networks to study language, right? And I mean, ultimately, again, as I said before, the goal for this course is to give you sort of instruments, tools, and approaches to study language, right? And so we're going to teach you how to do this, how to use those things, and you can apply it to language networks. Okay, so that's pretty much it for today. I thought I will actually have more time, and I'm going to talk, and that I would talk about some formulas. We're going to do it next time. To finish up, there is a book I would definitely recommend, which is a book by Network Science by Albert Laszlo Barabási. Google it. It's available for free online, and I also have it on my site. And then there are actually quite a few books which are collection of articles or papers on using networks to study language, right? And there is this book on structure discovery in natural language, and there is a graph-based natural language processing information retrieval. Those books, if you search long enough online, you'll find them, right? They're also, people put things online. So these are the books. Again, the first book, I would say this is a network science book. This is a must, right? That's definitely a must reading. The two other books, this is more if you want to understand how this is used for language studies. And interesting. And I think this is it for today. I'll stop here. Any questions? Okay, no questions. Look, let me stop the recording.